Hello everyone, welcome to today's lesson. In this lesson, we're going to be talking about two vector operations, vector addition and subtraction. We're going to learn that actually there is no vector subtraction. In fact, vector subtraction is another form of vector addition. So essentially the lesson of the day is just how do we add vectors graphically and algebraically. In case you need an introduction to what vectors are, you don't know what vectors are, please watch the other video I have on the channel titled Introduction to Vectors. And there I discussed what a vector is and how to represent it both graphically and algebraically. And just like that lesson where we went over vectors both graphically and algebraically, we'll go over vector addition as well, both graphically and algebraically. And the first method we're going to look at is going to be a graphical method for vector addition known as the parallelogram technique or the parallelogram method. In the parallelogram method, you place the two vectors that you want to add, in this case vector A and vector B, at the same origin, at the same starting point, and then you draw a parallel line starting from the end of one vector parallel to the other vector. So I go to the end of A and draw a parallel line to vector B. I go to the end of B, draw a parallel line to vector A, and where these lines intersect is the resultant vector. So I go ahead and draw a vector from the origin, from where A and B started from, all the way to where the two parallel lines intersect. So this is called the parallelogram technique. So essentially the resultant vector is this main longer diagonal of this parallelogram. So this is called the parallelogram method because in uh, drawing the parallel lines, you create a parallelogram shape, and the resultant vector will be represented by that longer diagonal in that parallelogram. We can also use another graphical technique known as the head-to-tail method to add vectors. And in this particular technique, you're not restricted to adding two vectors at a time. You can actually add as many vectors as you want all at once by doing the following. You start from the first vector. So in this case, again, we're adding vector A and vector B. So you start from vector A, and then you place vector B at the end of, or what we call at the tail of, vector A. So the head of vector B will be at the tail of vector A, that therefore the head to tail method. And then the resultant vector will start from the beginning or the head of vector A and ends all the way at the tail of vector B, at the end of vector B, or the last vector. So this is another technique we can use to add vectors graphically. Next comes algebraic technique, and how do we add up vectors algebraically? So here I have picked an example. Vector A in component form is 3, 3. Vector B in component form is -2, 2. And I'm adding these vectors. So adding these vectors, as you see on the left-hand side, using their vector equation, so A equals to 3i hat plus 3j hat, B equals to -2i hat plus 2j hat. And again, if you have any questions about vector representation and vector equation, please watch the other video I've posted about introduction to vectors. But assuming we know that I hat and j hat are the unit vectors, I hat is a unit vector along the x direction, positive x direction, j hat is a unit vector along the positive y direction, adding the two vectors together means adding the like components, adding the I hat components together and adding the j hat components together. So here, as you can see down here, then when I added the I hat components of 3a and b, I got 3 minus 2, which is 1. So that's 1 I hat. And when I added the y components, I got 3j hat plus 2j hat. I got 5j hat for that. And so our resultant vector will be I hat plus 5j hat, or in component form 1 comma 5, 1 comma 5. And as you can see in the figure, in the coordinate system, I've shown you vector A and vector B, and I've used the parallelogram technique to add them. And as you can see, the resultant vector, vector C, is at 1, comma 5. So this is how we can add vectors algebraically, by simply adding the like components, adding the I hat components together and adding the J hat components together. So on the right hand side, we have the graphical representation of this addition problem. And on the left hand side, we got the vector equation and how we can add up the vectors. Vector additions, by the way, come up all the time in physics and engineering, including Newton's second law, summation of forces equals mass times acceleration, where the vectors that we're summing are forces, basically Newton's second law. So, and many, many other instances, but that's just one example where we use vector addition. But what about vector subtraction? Do we have such a thing as vector subtraction? Is it a legitimate idea, vector subtraction? Well, one could argue there is no vector subtraction, quote unquote. What we really have is another vector addition. So let's take the previous example. Let's say A is still 3, comma 3, and B is still negative 2, comma 2, as you can see in the figure, and vector C, as we saw in the previous slide, is going to be 1, comma 5. When we add up A plus B, we got vector C, which was 1, comma 5. What about if we want to do A minus B? The critical thing here is that the first step in doing A minus B is thinking about minus B. Minus B is another vector equal in magnitude to B and opposite in direction. So as you can see here, the vector minus B is represented in yellow color here. And it's the same magnitude as vector B, 180 degrees from vector B. So if vector B has coordinates negative 2, comma 2, negative B has components 2, comma negative 2. So you multiply all the components by a negative sign. And then you just add, as you did before, components of vector A to components of vector negative B. All right. So here we have the I hat component of A is 3, minus the 2, which is the I hat component for B. So that's 3 plus 2, which is positive 5. And for the J hat component, for the Y component, we have 3J hat from A minus 2J hat from negative B. That equals positive J hat. So vector D will have components 5, comma 1. And as you can see here, using the parallelogram technique, we can see that indeed the correct location for D is 5, comma 1. So we can go ahead and add up vectors 2 at a time and add as many vectors as we like using this process. I hope you found this lesson useful. I will be following this lesson up with more lessons in physics, math, computer science, and chemistry. See you next time.